Okay, good afternoon, everyone, and thank you, Shilpaji, for the introduction and initiating the this course. And I was the first my was the first lecture in on 30 on when in on in August, I think.
16th
So
August.
16th August, right? And that was the overview, and I just spoke about various ingredients and various things which need to be considered in the conceptual planning stage for the buildings. And then thereafter there were several expert lectures on various aspects in detail. And today I will be covering this role of constructability and construction methodology in conceptual planning and designing of structural systems for the buildings. So I will try to cover everything within the time. So just to recapitulate, last first semester, first lecture, I talked about this the definition of a system. A system is a set of interconnected components or elements that work together as a whole to achieve a specific purpose or function. These components interact in an organized way, often governed by rules, relationships, or structures to process inputs and produce outputs. So essentially, we said there will be a set of activities, components connected together. There will be some kind of input and there will be some kind of a output. So this is a general definition of system. Then we also discussed about structural systems, how the structural systems qualify to be systems basically. So, a structure system is a powerful arrangement of interconnected members like beam, column, slab, foundation, etc., which are configured and constructed using the suitable materials, cross sections to resist and transfer applied loads safely to the ground. So this is output safely to the ground. Loads are acting on the system. This is input. It ensures that the stresses and deformations remain within permissible limits under all expected conditions. In addition to structural integrity, the systems must be economical, durable, sustainable, and constructible, balancing engineering performance with the practical execution and environmental. So this definition basically covers each and everything which we as a structural engineer need to consider in any design of any building or any structure. So then thereafter, I also discussed about the conceptual planning and designing. What is conceptual planning? So conceptual planning and design of a structure system for buildings is an early stage process before doing any detailed engineering, where the overall form, layout, and load-bearing resisting mechanisms of the buildings are conceived before detailed calculations or drawings are made. And basically, it is essentially about answering what kind of a structure system will make this building safe, functional, durable, sustainable, constructible, and economical while fitting the architectural vision. So basically, this is the scope of the conceptual planning and designing. So it is much different than the detailed design, because in the detailed design we base our design based on the conceptual planning, and at the conceptual planning we see holistically into all aspects of the building design and construction. So I also discussed this core ingredients for the conceptual structural system planning. I discussed that architectural intent is the probably foremost and the most important thing. What kind of form it is, geometry, aesthetics. Basically, here we need to interact with the architects and other civil engineers who are planning the structures, planning the building. So we need to understand and keep the architectural intent in mind, whatever we do in conceptual planning. This is very important. Then we also need to consider the site conditions, what kind of soil we have, what kind of bearing capacity, what is the water table, topography, seismic zone, wind exposure, all those things we need to consider. Then also we need to decide about the material strategy, what kind of material we need to consider, concrete, steel, timber, and all those things. And also about the cost. availability, sustainability, and also the compatibility with the architectural intent. Then we also have to consider the structural configuration, which is our core domain. That is about the selection of the system, like moment resisting, load bearing, or dual system, or whatever. And also we need to decide the grid layout, member orientation, and all those things based on the codes. And the load consideration, we need to consider all kinds of loads which are input to our structure system, which may be dead, live, wind, seismic, maybe static, concentrated, vibratory, cyclic, or any kind of load which may come on the, which are expected to come on the structure, and the combinations, all they are all to be covered as per the IS code. I think you already had a lecture on IS code and importance of the IS codes in the conceptual planning stage. We cannot say we have not considered the provisions of the IS code or some other standards in the conceptual stage, and hence it is not possible to do now the detailed engineering, and we are finding difficult. We cannot say that. We have to consider this thing at the conceptual stage itself. Then this is a construction methodology we will discuss in detail today. So basically, we need to consider the feasibility of erection and sequencing, whether prefabrication or in situ construction, speed, safety, labor skill, all those things we need to consider. Sustainability and life cycle, we already had a detailed lecture on this aspect to be considered in the conceptual planning stage. Our concept structure system should be such that it should have the minimum embodied energy and the carbon footprint. It should also be durable, and maintainability should also be there. And there should also be flexibility for the future modification, for reuse, for sustainability. This is also an important aspect to be considered. And then regulatory and code compliance. This is non-negotiable. We have to consider structural safety, fire safety, and local building code standards we need to consider. So we also discussed about the key steps which are there in the conceptual planning and designing stage. These are: understand project requirements, review architectural concept, assess site and environmental conditions, choose the structure system, determine the column grade, beam, span, column core locations, foundation types, decide upon materials, steel, RCC, wood, composite, codes and standard provisions, coordinate with other services, then availability of materials and expertise at site, development of the conceptual structure drawing. These are the steps which we need to consider and in the conceptual structural system planning stage. And this is the output of the conceptual stage. We will have the structural layout drawings, which will show the grids, core, load-bearing systems, and the structural system adopted with rationale, whether it is a SMRF or structural walls or any other kind of a system. Then prelim size of the key members. I think we will have a lecture today. We have a lecture today after this, how to calculate the basic sizes without going into detailed computations. Because unless until you have this kind of a thing, it will be very difficult for other consultants and other discipline engineers to work upon our concept plan. And then there has to be a integration between different services. So today we will be discussing the constructability aspect. So what is constructability? So I think we need to understand this also very carefully. What is constructability? Constructability refers to the integration of construction knowledge. Okay, integration of the construction knowledge and experience into the design process to ensure that a structure can be built efficiently, safely, and cost effectively. So here focus is on design, feasibility, and efficiency. So when we are doing conceptual design or planning of structural system for a building, we need to understand based on our construction knowledge and our experience, whatever how it will be useful and how it can help in our structural planning stage. So our focus is on design, feasibility, and efficiency. So it reduces the rework and also improves safety. Early stage decisions are required for constructivity. So basically, we cannot or we should not decide any structure system or conceive or plan any structure system which is not constructible or which is difficult to construct, because it will be costly, time consuming, may lead to a lot of contractual issues also later on, apart from safety issues. So the next part is the construction methodology. This also we will consider today. What is construction methodology? This is a strategic plan and sequence of operation used to carry out the construction of a building. Okay, so how the building will be constructed, what will be the sequence of the building, what is the strategic plan? This will also affect our conceptual planning. This also we need to consider. That is why I always say a good structural engineer is not the one who know the codes and the basic fundamentals and the theories. He must also know how the buildings is constructed at site. Okay, so focus here is on processes and the sequencing. It impacts site operations, site logistics, and detailing needs to be considered in the structure planning stage. So whatever is the construction methodology to be adopted, we need to consider how this is affecting our structural detailing or planning. This is construction methodology. So construction methodology is a little different than the constructability. And then third component is construction technology. The construction technology is basically about the tools, materials, and the systems and innovations used to execute building construction. So, suppose somebody want to use a 3D technology, that is a construction technology. Somebody wants to use a precast construction, that is a kind of a technology. So somebody want to use a particular kind of a formwork, say my one formwork or tunnel formwork or any other kind of form. That is kind of a technology. So we need to consider the tools, materials, and the systems used to execute building construction. So focus is on tools and innovations in construction. It will enhance speed and also the better quality. From design point of view, all we need it deals with the material and the system selection. So these are the basic thing about the construction technology, construction methodology, and the constructability. Okay. So now let us see the considerations of construction related issues. What are the various considerations of construction related issues? The first thing is choose the materials not just for the aesthetics or the performance. We as a structural engineer generally try to choose a material which are structurally efficient for a particular project. And the architects also want the structure, the materials to be such that they are aesthetically pleasing and they suit the architectural form and architectural vision. That is important, true, but we also need to consider their availability at site and the ease of handling and the local construction practices. So there is no point of using a material which is not available at a particular site. For example, there is a hilly area or there is a remote area where you want to construct some building. So it may not be possible to have good quality bricks available there, or a exposed brick construction possible there. Local stone may be available there. Uh, so so we should specify and use only those materials which are available, which are easy to handle, and where the people are there to use them. not only from aesthetics and the performance criteria. We often ignore the site constraints or the site requirement for the material. We need to focus on this. So, for example, opting for precast concrete panels over complex cast in situ forms to reduce labor and time. This can be a consideration during the conceptual planning stage. Deciding on kind of masonry to use, whether you want to use the brick masonry, stone masonry, you want to use AC blocks, or what kind of, depending upon the availability and expertise available. It is no point to transport a material from a long distance, which is going to be costly, unless until that is not negotiable. There might be a situation that is non-negotiable. Whatever may be the cost, we have to use that kind of material. If that is a situation, then things are different. And then we have to decide whether to use a high performance concrete, normal concrete, RMC, or site batch concrete. Whether site batch concrete is possible, whether RMC plant is available nearby area or not. All those things we also need to consider. Whether we should have a batching plant at site, or whether we should procure the concrete through RMC, and then whether we should use the steel rolled sections or the cold form sections. Further, in difficult hill areas, using stone masonry for retaining wall may be a possibility instead of RCC. In coastal area, use of FRP bars, rebars, epoxy coated steel or stainless steel may be an option. We have to decide at the conceptual stage. And then in hot and dry climate, use of lime, cement, stabilized bricks, earth bricks may be considered instead of concrete blocks. So all these are there can be n number of possibilities which we need to consider at the functional conceptual planning stage. And then another important consideration is the site access and the logistics. It can affect the choice of the structural system itself. Now, suppose in a congested urban site with a limited laydown area, probably the prefabricated steel components can be trucked in the and lifted quickly using the mobile cranes, cast in situ concrete with the formwork, which require curing and all those things, and the time required for the setting may not be a good option. So, depending upon the site, whether we have access or not, and what are the logistics available, whether we can construct the basement in a congested area, whether we should go for top-down construction and all those things. So we need to decide at the conceptual planning stage. Site access and logistics will have a very serious and bearing on our planning. Similarly, cranes reach and lifting strategy. Suppose we are deciding that we want to have a precast construction, and your site do not have and they are quite long panels and heavy panels, and you need cranes which are very heavy cranes and having so there is a possibility that you may not have the space where these kind of cranes can be used. So before starting or deciding a system without looking into the site constraint will be really a rework, or we need to modify the design later on. So we need to consider how the metal will be lifted and how the strategy can be applied. So, like similarly, in such a situation, we need to consider whether timber or light gauge steel can be considered for low-rise building, particularly because heavy, which can be used with the light cranes or small cranes, or maybe hand handling, manual handling may be possible. So we need to consider this aspect also. Then the construction sequencing and the speed. We all know the modular steel systems allow parallel fabrication and foundation work. There's a possibility that we can have a pre-engineered building systems, or such kind of a system where you can have the foundation work going on at a site and other things are going on off-site. So if the construction sequencing and the speed is required, then probably you will like to have a different kind of a system, because cast in situ concrete construction system are slower and they take time. And also there's the weather dependency on such systems. So if it depends upon the client requirement, what kind of sequencing they are looking for and what kind of speed of the project they are looking for. We need to consider that also during our conceptual planning stage. I'm highlighting these points because often we ignore these points and we just think what is the best system which we can have, which is structurally efficient and the codal requirements fulfillment point of view. So modularity and repetition, yeah. So when we are planning a building at a conceptual stage, I think it is always better to have a repetitive grade, uniform grades. They will simplify the form work. If you have a grades which are not uniform, definitely they will require a lot of different kind of a mode and form works, which may be difficult to construct at site. It will reduce because repetitive work will always reduce the errors and there will be speed up of the construction and even the cost will also be less. So if we can do, we should definitely think of modularity and the repetitive grid system. Because irregular forms and grid requires custom molds, complex sequencing, and skilled labor, reducing constructability. Another important thing is structural element sizes must be as much uniform as possible because if you have in any building large variation in the column size or large variation in the beam sizes in terms of sections, then really it is very difficult to have different form size and it is very complex and difficult to construct. So rather it will be better to have as uh, s- as less variation as possible, and it is always better to play with the reinforcement. You can always increase decrease the reinforcement and the concrete grade. So I think that is a better choice rather than changing the having the variation in the structural element size. I have seen yesterday only I was seeing a building, a really large building, and they were using around 15 to 18 type of size of the beam with minor variations actually. So that kind of a scenario doesn't make much sense from construction point of view. Theoretically, it is okay. Design point of view, it's okay. Codal provision satisfying, it's okay. But from construction point of view, it is difficult. So we need to, when we are doing conceptual planning, we must think from the angle of a builder or a contractor or a project manager. Only then our design will be more constructible. And then we also need to see the labor skill and the local expertise available. Now, for example, for a small construction, there may be a possibility that in a remote areas, particularly in hilly area, where there is an inaccessible area where probably timber may be a good choice to construct buildings where timber is locally available and people are generally used to using it. They have expertise in using it rather than bringing different kind of a material, concrete or steel or anything from a far-flung area. So we need to consider what kind of labor skill and local expertise is available at a particular site. So another important consideration during planning stage, which is construction related, is the optimizing the complex geometries for buildability, which can be achieved in collaboration with the architects. Suppose you have a building which has been conceived by an architect which has a very complex geometry in terms of shape or the curves or something. So, which may not be structural friendly and which may also not be the construction friendly. So, as a structural engineer, we can always have a dialogue and the collaboration with the architects, and we can suggest modifications, and we can have some kind of a we can have some kind of optimization in the geometry so that architectural intent is also maintained and also we satisfy the requirements of the codal requirement from a structural point of view and also construction becomes little easy. So this is a very important thing. It is not that whatever if somebody has conceived, we have to just fit in into our structural thing. So it is not necessary. We must have a dialogue. Uh, so basically, this aspect will reduce the formwork complexity. It will simplify the shapes. It will lower the need of the intricate molds. It will save the time. It will minimize the custom fabrication. It will also streamline the procurement, labor training, and the quality control, and also probably the structural efficiency and the performance of the structure will also improve if we try to do that. But it depends upon how knowledgeable we are, how persuasive we are, and how positively we are collaborating and having dialogues with the person who has conceived the basic plan. Then we also need to have the risk reduction by identifying and considering the constructability issues at the structural planning stage. So basically, we need to identify bottlenecks before they cause costly delays. We need to mitigate safety hazards through better sequencing and access planning. We need to avoid rework by aligning design intent with the construction feasibility. And we have to enhance the resilience by anticipating site-specific challenges like soil conditions, weather, or logistic. So in this picture, you see a building which is standing, the 4 5 story building, and then a basement is being dug for a new building very close to a existing building. So we need to consider, because this is a risk to the adjoining building and also to the people who are working at the site. So we need to consider how this kind of a situation should be tackled beforehand at the conceptual planning stage itself. So we need to do something. We need to have some kind of a diaphragm wall or some kind of a sheet pile or some this kind of provision we need to take during the. We need to consider this aspect before we go into the detailed uh, designing stage, because if we ignore this and we just simply design a building ignoring what is happening at the site or what is existing at the site, it may lead to really very serious safety hazards. And this kind of a situation is happening day and night all over India, particularly during monsoons. I get almost 4 5 calls every season. This kind of when somebody is building nearby existing structure, particularly during monsoons, and so we need to consider this really very seriously, how to take care of the risk due to the site challenges. So there are the options available. We can have a diaphragm wall, we can have sheet piling, or we can have some other measures, or we can even if required, we can even we can change the plans also if required, or we can do something else. But we should know what are the issues. So there's a risk reduction by identifying. We can also consider using BIM and 3D modeling, the advanced technologies, to simulate the construction sequences and also see where the clash are happening. And we also need to involve the contractors, the site engineer, the PMC or owners engineers during schematic design itself. We should not consider that we are the expert and whatever we are designing, it should be constructed. Okay, that will be constructed, should be constructed, but whatever we are designing, that should also be implementable. That should also be construction friendly. So we should also take care of the views of the contractors and the site engineers if and consider all those issues in the our designing stage. And whatever the constructivity issues we get, feedback we should document that, and we should prepare a report based on that. So many times we will be designing something which may not be theoretically a perfect solution, but we are designing something which is perfect solution for a particular situation. So that is important. Then planning, expansion, seismic, separation, and construction joint with a consideration of design as well as construction point of view. See, we all provide expansion joint or some seismic joint or whatever. We know where to provide, how to calculate the width and all those things, and should be the distance between the two blocks and all those things. We know all those things from design point of view, that we know. And we but this thing also have a impact on the construction sequence. So if we have a building and somebody want to construct in a say 2 or 3 stages or three phase, so probably we can provide joint not only from design point of view, but we also need to consider how the construction is being taken up, what is the client's requirement, and based on that we can adjust or plan our joint, because that joint will also help in the construction. So this thing will help in structural flexibility, seismic resilience, fire and safety and the zoning, architectural flexibility, phase construction, possibility of repetition of resources. So just by suitable planning of the joint itself will help in so many aspects. Then another important aspect is the kind of the formwork we are considering to have. So specialized formwork like aluminum formwork or tunnel formwork and the slab form or whatever don't just accelerate construction. They reshape the way buildings are structurally planned under design. So the kind of homework we intend to use, or the builder want to use, or the owner intend to use, so we need to consider in our planning stage. This system should be considered early in the design phase, as they influence everything from layout geometry to load paths and the reinforcement detailing. So specialized homework decision needed at the stage of conceptual structural planning, and there will be standardization of the structural elements, monolithic construction, early coordination with the MEP, speed and flexibility trade-off, precise alignment and reinforcement detailing need will be needed. Then early strength gain for rapid cycle time will be needed. I am highlighting this point because these things will be affecting our decisions. So we need to know what kind of homework we need to use in our building. And then this is another, I think I'm about to finish my presentation. So you see this picture here. Conceptual structural planning is not just about sketching load paths. It is about anticipating how design choices will play out at site. Very thin sections and higher percentage of steel may satisfy the structural requirements as per the codal provisions. Okay, but they may lead to poor construction quality, concrete quality due to steel congestion, particularly joints. You can see how much steel you have. This is a hypothetical picture, but you can see many times you can see this kind of situation at site. So much reinforcement, particularly at the joint or the thin sections where even doing concrete is really a horrible task. So we need to consider not only the codal requirement, but from practical construction point of view. So it is always better to have little larger column sizes, and we have to pay attention to the beam column junctions, and probably the percentage of the steel we are using in our work. So delays it may have lead to the delays and the rework during construction. It may lead to honeycombing. It may lead to the so many other things. And so increased cost due to labor intensive activity and material, because placing reinforcement, something like this, a really very difficult task. So we need to consider this aspect also while deciding structural element sizes during the concept planning stage. Okay, afterwards you will do the detailed designing. Thereafter you will do the refinement and you will do the detailing. But at the conceptual planning stage itself, we must be able to decide tentative size which are feasible, which should not lead to this kind of a situation. That is important. So, okay, so I think a structure is not just designed to stand, it is designed to build. Early constructability reviews turn vision into a reality. with fewer risks and greater confidence. Thank you.